Hello everyone, this is the third Venom developer introductory session, and today we are going to dive deeper and get our hands dirty with smart contract development. But firstly, let's recap what we had in previous session as a result. So we have our contract, we deployed it to testnet, we learned a bit about how locklift works, how locklift config is structured. We learned how to use Explorer tool, how to look at these fancy diagrams which we have for each message, so that we know how all the message chain worked out and what methods were called. And also we touched a bit tools.venom.rs, which is a fancy debugging tool and automatic UI generator for your contract, so that you give them an address, you give it an API, and it renders the UI with which you can interact with your smart contract. Today we are going to learn a bit about how Venom blockchain works, the types of messages. We'll learn a bit about what buttons we need to push in what circumstances here, and also we are going to modify our contract so that it will be a bit more functionality, and also we will understand the important security aspects of writing smart contracts, and also I will give you a entry point where you can learn more about differences between TSOL and traditional TVM Solidity languages. Before we start, I want to remind you that on the Venom.Foundation website you can subscribe on our social media channels where you can be in touch with our announcements and news. So yeah, let's proceed. So yeah, at first, if you want to skip everything and dive deeper on your own and learn it by yourself, feel free to go to docs.venom.foundation. In the section Build, you have Tools and Resources, and here you have all the developer ecosystem products which we have. And for today's session, the important one is TSOL API. So yeah, let's make a short overview here. So TSOL is very much like Solidity language, but it has different mechanics and also additional mechanics and data types. And this document, api.md, outlines the whole specifications for all data types, for all intrinsic functionality, and how each feature works. And 50-50% it inherits from Solidity, but another 50% is Venom specific mechanics and data types, and also functionality. Just for a little example, we all know the mapping data type, and in TSOL the mapping API allows you to do much more stuff than Solidity has. So you can iterate on mappings, you can calculate the minimum or maximum value from mapping keys, you can do fancy functionality, make some checks, and make some optimized operations, like for example get set or get add or get replace. So yes, I highly encourage you to dive into this document and learn more about what functionalities we have. Especially in the TVM namespace, because it's fully Venom specific. Also, mathematics namespace is built in as opposed to Solidity, EVM Solidity API, where you have mathematics library. So here the secure math is built in to compiler. We have also random number generator, just for you to know. So yeah, so there are a lot of interesting stuff, and this is a very good entry point to know more, and really I believe that you become a fan of Venom just by reading this api.md, because it's really developer friendly language and provides a lot more tools than traditional Solidity provides. Still, it inherits the original Solidity specification, so the syntax and the developer routines are totally the same, but there are just a little bit differences in semantics, just because of Venom is a synchronous chain. Alright guys, before we get started with some coding, I would like to introduce you a little bit of architectural concepts of Venom chain. So instead of function calls, we have messages, and everything basically is any logic is launched by messages. And in Venom you have three types of messages. The first one is external incoming message, which is the message from user from the real world inside blockchain, inside some account. And it's important to understand that there are no externally owned account. So this message carries no value. It just may or may not carry a signature and some additional information on developer's choice. For example, the time, the pub key in case if the message is signed, and some payload, which basically says what function needs to be executed. The second type of message is internal message. The internal message is a message from one smart contract to another smart contract, or from one smart contract to itself. So it is allowed to make a recursive message sending. And inside the logic of your smart contract, within one transaction, you can send up to 255 internal messages to other contracts or to the smart contract itself. This is the internal message. And these messages always carry some value, because you need to pay for network. These messages are asynchronous, so in order to get some result, you need to send message back from the contract you want to read. The third type of message is the event, basically. This is called external outgoing message. So this is a message from smart contract to outer world. These messages are written to blockchain. They're pretty much like logs in EVM, but they're not stored in separate storage space, as opposed to Ethereum. They are also included in blocks in the same fashion like messages, like internal or external messages included in blocks. And these messages basically just don't have destination addresses, and they don't trigger any logic. This is just a shutout to outer world. Speaking of syntax, it just works like an Ethereum. So you're emitting some event, you're declaring some event with some payload structure, and then you can emit the event and say something to other world. In the sample smart contract, when set state function is executed, the smart contract emits like, hey, the state changed and now the new state is this. All right. The second thing I wanted to say is that basically what we are going to fix and what we are going to introduce in our smart contract is we are going to make it more secure. For now, the logic of smart contract is vulnerable and anybody can drain the account's balance. Because the set state function is public and there is no signature check or authorization, and the very first line of this function says TVM.accept. So this instruction translates to accept TVM instruction, basically, and it says, like, since this line, any logic which will be executed after this line will be paid by current account. So this is very insecure to put this TVM.accept wherever you want. You only should put that after you checked that the message which triggers this logic is the message you actually expect and you are ready to pay for. So the first thing we are going to introduce is, instead of using just a random variable nonce, which, as I told in previous video, is needed to be able to deploy several instances of this contract, because the address is calculated deterministically from static variables. We are going to introduce the owner, and the owner is represented by pub key. So the owner is not an address, it's just a pub key, an identity, and the static variables are initialized on the deployment event. So once you deploy the sample smart contract, you put the pub key of the future owner of this, and let's design our system in such a way that there cannot be the same instances for the same owner, because if we try to deploy this contract twice, the address would be the same, and once it's occupied with some code and data, you cannot deploy anything to this account. So yeah, so now the address of our contract depends on the owner variable and the smart contract code. Right, in the constructor function, we need to verify that the actually or no, yeah, no. Right, so the first change we are going to introduce is to make this setState function secure, and for that we are going to make a require statement which will check that MSG pub key equals owner, and here we need to put some error code, so let it be 101. Right, once the msg.pubkey equals owner, we can allow to spend the smart contract balance. Right. The second change I would like to make is to allow this smart contract to change its state by being called by someone else who will pay for that. So for that, we will introduce the function setState by anyone. It will also accept uint state, external, and there is a built-in modifier is internal MSG, which checks that the message is internal. By the way, we can put here the is external MSG, so that we can be sure that the message is actually external message. And yeah, and here we don't need to do TVM accept, because we just need to check that incoming message has enough value to pay for state change. So let's check that MSG value equals, for example, one Venom, right? And let's throw the 102 error if it's not so. And I'm going to rename this setState by owner, and I'm going to introduce some private function setState, uint state private, which is where I'm going to extract just this piece of logic, so that we can reuse it. Right, so here we will call setState with this parameter, and here we will also do the same. Right, let's try to build our contract. For that, I'm going to just run npx lockleft build. Right, what's wrong here? Declared Okay, let's check. It seems that the right syntax is this, yes. Yeah, so that even the syntax highlighter told me that is correct. So let's try again. MSG pubkey equals owner, not compatible with types, good, and alright. Let's check it out. MSG pubkey unit. Alright, let's I forgot to put parentheses here. Alright. Okay. Okay, we built our contract. So how can we be sure that it works actually? Oh no, I forgot to add some another change. Let's make our logic a bit complicated so that I can illustrate how tests basically works and how to write tests. So let's also check in the set state function. Let's check that the actual state that we get is not more is less than less or equal than 100. Okay, and let's raise the 103 error, for example. Okay, I'm going to put that down. Okay, let's rebuild it again. Cool. Okay, so we have our modified contract with a few additional features inside it, and we need to make few small changes to our environment. So the first one is that we need to update our deployment script because we don't have the nonce variable in static fields, and the syntax highlighting shows us that actually. So let's put the owner here, and the owner would be the same pub key that we used to deploy. So that would be signer, public key, and let's add 0x before that so that it will be understood as a number. Alright, the second change I want to make is to put the seed phrase from our Ever wallet explicitly to keys section so that the owner field would be set as the same key as we have in our wallet, so that we can touch this contract through our wallet and demonstrate the ownership basically. So yeah, let's try to deploy. Okay, we have the address. Just follow the same steps as we had in previous session. So we go to Venom tools, put the address here. Our ABI changed, so we get that from build artifacts. Just copy paste that to Venom tools. I'll call it sample2. Right, so we have generated UI for our contract, and yeah, in the transaction history we see that we successfully deployed it, and the event was emitted with state 0, so everything is good. Now, and let's try to test all the features. So the first one is get details, running that method locally and see state is 0. Alright, let's try to set state by owner. And this, remember that remember that this method accepts only the external messages. So we need to sign the external message. We need to send the external message here, and for that we push the button send external. Typing in my password here, remembering it so that I won't need to type it again. Oh, I called it with 0, so we basically won't see if it succeeded. So yeah, let's put it to 42. Right. All right. So in the transaction history, we see that state changed to 42. Let's try now to switch our wallet to the new account. Basically now the owner of the sample contract now is account 1, and this sample owner, the new account, which has different pub key, we are going to switch to this account and try to send the external message with that. So I'm typing in my password again. And now the expected result would be the error. So what happens now? We see that the UI is frozen and it doesn't tell us anything. That is because the external messages which don't execute, basically, which cannot pass the check inside smart contract. These messages are not included in blockchain. So now we see that basically this message ran out of timeout, and after maybe 10 seconds we see that that nothing changed, and in the transaction history we also don't see anything, even the error. That's because such an external messages aren't even included in blockchain. So let's refresh and try to oh, I need to reload the API. Oops. Sample. Maybe I can choose it from. Okay, yeah, I have sample too. All right. So let's now switch to the second functionality, which is set state by anyone, and shortly overview the code. So remember, we put the internal MSG modifier here so that we expect this function to be called by some other smart contract, and now we will see how we can call it using our wallet smart contract. And it also requires the message value to be more or equal than 1 Venom. So let's try to change state to 1. I need to put some money here, so let's just transfer. Oops. Let's just transfer, I don't know, 10 tokens here. Okay. Now we should already have that balance. Okay, we have it. Now let's try. So to make the internal message call to some account, we need to push the send button here. So we have 3 buttons. We have run local, which is for reading states and calling so-called getter methods. We have send external button which sends the external message optionally with signature, and we can sign it with any wallet we have in our we can sign it with any pub key we have imported in our Venom wallet. And also we can push the send button so that the call will go, so that the external message will go through the wallet smart contract, and then the wallet smart contract will forward the message to our target account. So now we are going to put, for example, 0.5 tokens here and push send. Alright, so what we see here is the transaction was aborted, and the state remains the same. We can check that separately. So the state is still 42 because the balance, the message value we attached to this message was less than 1 Venom. So now let's attach 1 Venom and see how it works out. Alright, now in the transaction history we can see that our state changed successfully. So now there are no errors, and basically that proves that our smart contract works. Yeah, let's test also this functionality of changing the state to, for example, 1001. Also with 1 Venom, and that should also raise the exception because of the value is more than 100. Alright, we see that exit code is 103, which is what we expect. And when running get details, I see that state is still 1. But I'm not sure that this is a comfortable way to test your smart contracts, especially when they are complex. So we are now going to write some automated tests. Actually, I prepared some tests for this smart contract, so do not bother you with typing. So let's review that. Alright guys, so here is my test file. It's about 100 lines long, and before I wrote it, and before you write your tests, please make sure that you have these 3 lines in your locklift config, which will enable some batteries in Chai framework, some batteries related to locklift, and a bit later I will show you what exactly I mean. So the structure is pretty simple. I have some helper function to deploy my user to emulate some user behavior. I declare some variables which I'm going to use throughout tests, and I have actual tests. So I have 4 tests and 2 functions to prepare the tests. And the first one is I get my signer, so that will bring the pub key for deployment, and also I get my another signer with another index to deploy the user account. And here actually I use this helper function to deploy this account. So I deploy it with 5 Venoms as initial balance, and with this signer I'm going to call external external message, call functions with external messages, and with this account I'm going to invoke functions meant to be invoked internally. Then the test scenario goes. So the first one is I check that I have all my build artifacts. So I use get contract artifacts for my sample contract, and I'm just checking that code, ABI, and binary file actually are not undefined, so they exist, and I proceed with deployment. Then I go with deploy procedure, which is pretty the same as in deploy script, but here I just put this expect line in the end to make sure that the balance of the deployed account is above 0, so that I'm sure that account is actually deployed. Then the first tests checks the first two tests check the behavior with external messages. So I'm going to also I have and also I have two tests to check the behavior with internal messages. So let's go through it. The first test is invoking the setStateByOwner method with signer pub key and checks that the state changed to the new state. That's pretty simple. The second one is a bit more complicated. So here I'm memorizing the previous state and trying to set the new state to 101, which expected to fall and to raise some error. So I'm invoking the same function with external message, and checking that the state did not change. The third test goes a bit deeper, and for that we use this user account. So how do we do it? And also here we use the tracing feature of Locklift. That's why we put that 3 lines so that Chai framework can have some can work with so-called trace-tree variable and enable this Chai in Chai this expect checks in Chai fashion. So let's go line by line. So here I'm also memorizing the previous state, declaring what new state should be. Then I'm setting up the tracing module to ignore the 102 error, which is the error code for wrong amount in internal message. Then I do the same thing as I did here, but I'm wrapping this method call with locklift.tracing.trace, which will give me a trace-tree variable, and then I'm printing that trace-tree. So when we run the test, we will see how it looks like. So it's basically the same as a diagram in Explorer. It will show you the whole chain of messages which are produced by the first external message. So and when and notice that here I use send external, where I specify my signer pub key, but here I use .send which expects two parameters, the from and amount, and the from is address of the account where the first external message should go and which should produce the internal message to our smart contract, and the amount is the amount which I'm going to actually attach to my internal message. So here I'm expecting my contract to raise 102 error, and this line does that, and then I'm checking that the state did not change. The last test is positive test. So I'm just changing the state to 4 and put the correct amount here, so it should be greater or equal than 1. And I do the same trick with trace tree just to see that my message chain visually in the console. And then I'm checking that the state actually changed. So let's run the tests. Now we are going to see this tracing, how tracing module looks like. So we see how the chain of messages worked out. We see that we first put the message in the Ever wallet, and then Ever wallet contract passed this message to a sample contract, and the highlighting in red shows that we basically met an error, and the error code is mentioned here as well. It also have all the details how gas flows in this chain. So once the error was met, we bounced the remaining gas back to our wallet. And the next test passed successfully, and here we see also pretty printed trace log of all of how message flow worked out. So the incoming message was an Ever wallet, and then went to sample, set state by anyone with correct value amount, and then event was emitted by sample contract with state changed to 4. So yeah, so all our tests pass well, but we see that it worked out a bit long. That is because we use production network, or basically test network. So to run your tests smoothly and fast, we may want to use some kind of local node. And now I will show you how to install that local node and run tests on local node.
Now I'm going to check if my Docker is running. So I have this dashboard, empty dashboard in Docker. It should look like, if you install the Docker, it should look like that. Then I'm going to paste the command which will pull the Docker container of local node. You can easily find this command on docs.venom.foundation. So I'm going just to run it. So what it means basically, it just pulls the local node from the tonlabs/local node repository and runs the container, which will also spin up the local explorer on the 18th port, so that you can reach this explorer in your browser just typing in localhost. Now let's run it. So we can see that you can find this image locally. So it's started automatically pulling it from tonlabs repository. Let's wait a bit. Okay, once pool is complete, I'm going to show how Local Explorer looks like. So it's running on localhost. You can see a website with some blogs, messages, transactions, contracts. There are 4 contracts. One of them is your local giver, which is already configured in your localhost config. Let's run our tests. I'm running npx log flip test, but I replace the network parameter with local so that it will run against local node, and we see that all tests passed in a few seconds. That's how do you work with local node.